Recording started. Okay, please, Group A, go ahead with your presentation. We are all waiting to hear from you. Hello.
I will share the presentation. One moment.
Let me ask you, how did
Yes.
you work on the presentation yesterday?
We worked together on the presentation. Everyone did their own part, but we were not sure yet if we had to deliver it or to make it already this week, as there's no deadline yet for the challenge 2 in E3.
Yeah, but it's always the same, right? We are 2 weeks on, 2 weeks off, right? So
yes,
every time there is a submission. So no, my point is that the Canva was down yesterday.
Mm-hmm.
Did you notice?
Yes. Mm-hmm. But we managed to do it all together with the whole group, so that's nice.
Yeah, we also had to submit a very important presentations, and Canva was down, and we were panicking because, of course, we don't have any local copy of the presentation. Okay, just moment in history, right? Because AWS went down. Did you see? AWS went down.
It causes big trouble. I think, at least in Europe, it causes big trouble.
Okay,
and
very good.
Shows how dependent we are on like American companies in Europe. I think
all the world is in the same. Yeah. Where are you from in Europe? Remind me.
Holland, the Netherlands. I'm from.
Yeah. Let's not specify the political situation. The Holland is in the Netherlands, it's in the Flanders. That it's always very confusing for me. Yeah. Okay. Good. Yeah. Yeah. I was there. Actually, I was at TUE last year, but I don't know where TUE falls in your political organization. But anyway, yeah.
And we now have to choose our new political leaders. I think it's next week for the upcoming 4 years. So it's now quite important.
As a topic, yeah. I think so. Yeah, America is becoming very unreliable as a geopolitical part. No, but it's just, so how does it work? There is so you guys, so the countries, Benelux? No, how does it work politically?
It's Holland, just the Netherlands, like no Benelux. It's like we don't really work together with Belgium and Luxembourg, but there are some small things we do together. Like we have lots of business with Germany and Belgium, and Luxembourg is really small, but it's so we are just doing lots of companies are working together from both sides.
Politically, there is no agreement or no. Right?
No, there are no political agreements. We are totally separate.
So why do people call it Benelux?
I don't really know. We are just close to each other. The Benelux are countries which are near each other, but political, they don't have any influence on each other.
So you're saying that only economically there is some free trade agreement beyond the European one, right? That's what you mean?
Yes, it's like the EU. It's almost the same agreements as the whole EU has at the moment. The European Union. There are no special things, I think, between the countries.
Yeah, okay. Just for the other people that are not European, because also every European wonders what happens up there, right? Because they have like 3-4 countries, but then it counts as one. It's very confusing for us. Anyway, let's get to the challenge, please.
Yes.
Please go ahead.
Challenge. We have done research to Poisson regression. We started with linear regression, the baseline model. We made the linear regression model, as you can see on the graph.
Let me stop you a second. Let me stop you a second. Going back, why do you think I gave you this type of problem? Why do you think? What was the logic behind it?
I think you wanted to show us why linear regression isn't working. We have to research why linear regression is not a good model for this case.
Correct, right? Because if you have something which is like a count, which is like an intensity, which is a positive defined quantity, then you cannot use linear regression, because linear regression is going to give you negative estimates, possibly, right? So It just doesn't fit. And that's why I wrote a message in Slack. I was like, oh, in my mind, there were two things that I wanted you two guys to look at. One is recursion, right? Periodicities. So, when you see a lot of temporal data, right, then you see monthly and weekly and daily periodicities. When you do, let's say, when you do some weather prediction or some electrical load prediction, blah, blah. And the other one was this one here. So I chose this one here just to show you guys that, the limits of linear regression. Go ahead.
Okay. Linear regression model. We made a linear regression model. As you can see in the graph over here, the red dot line is the line it should follow or approximately follow, but there are lots of differences compared to the red dot line, so you can see it's not a suitable model at all. Furthermore, we used as predictors all the predictors that are in the model. We used alcohol, sulfates. Yeah, I can write it for you, but it's not important. And we made a standardized coefficient of these predictors, so we can see which predictors has a major influence on the end result. The biggest influence are with alcohol, sulfates, volatile acidity, and total sulfur dioxide. And in further research, I would recommend to leave out the other predictors, as it makes it more complex, and there's a bigger chance on multi-collinearity, and some predictors don't even have a real influence on the result. There's like a really small influence, but that's more accidentally, because never the value will be 0.000. Wait, sorry. Yes, there we are. Evaluation of the model performance. We use mean squared error and R2 to as evaluate. We came to a mean squared error of 0.42. That means like the residuals are approximately 0.42 per data point, like to the predicted values. And we used R squared, which came in at 36.1% percentage of variance is predicted by our model. As you can see, it has approximately a normal distribution. It's skewed to the left, which, as you can see in the QQ plot and in the normal distribution plot. This means that he doesn't predict the low values, like all the values right. Mainly the residuals for low values are not predicted right for the negative values. Furthermore, the limitations and conclusion. The limitations of our model are that it's heteroscedasticity. That means there's a big difference in there's like a big difference in variance per value. Like for lower values, there is not the same difference in variance than for middle values. The residuals don't follow normal distributions. It's skewed to the left, and besides, we use too many predictors, which overfits the model and makes it more complex. For this reason, we do not think linear regression model is a good model, as it has heteroscedasticity. It has integers, and the linear regression model is for continuous values. And it is not totally normally distributed. For this reason, we will recommend a Poisson regression model. Now I want to give the word to my colleague.
So next we'll be talking about Poisson regression fundamentals.
Yes.
Next. Yep. So we'll start with a likelihood function. So this function is actually provided in the document. So firstly, we do a log transformation. And eventually, the log yi factorial does not depend on beta, so it can be removed.
Just a second, slow down. Spend a little bit of time on this. Can you go to the previous? Yeah. So because I don't know what is the statistical background of the class in general. Yeah, if you can just describe this a little bit. Yeah, go ahead. So the L of B, what is this? That's a likelihood. Go ahead.
Yeah, so the small L of B is the log likelihood function of beta. So eventually we are trying to maximize.
Which is this, but that comes from, that's the, okay, tell me a little bit more, right? So there is an e to the minus lambda I to the yi divided by yi factorial. This is the
Sorry again.
So the expression e to the minus lambda I to the yi divided by yi factorial. This is the TDF of a
Poisson distribution.
Very good. And then what do you have the product of?
Good. Wait,
Okay.
sorry.
So here you have a summation of the multiplication of a yi. What does the multiplication of the yi correspond to?
I'm not very sure.
So here, let me. Okay, so this is for everybody, right? So the idea is this: you have yi observations, and these yi observations are assumed to come all from the same Poisson distribution with parameter lambda I, right? So so the idea is that if you observe a certain set of yi, the probability of observing the sequence of the outcomes yi is the product of the probabilities, because the observations are all IID, right? Then, of course, we don't like to work with products, so we take the log, right? And when you take the log, that turns the product into a summation. And then you bring the log to the argument of the summation. And inside the argument of the summation, you have these other terms. So you apply the log to this product and ratio. And so you get this exponential coming in. And then, yeah, that's how you get to the small L of B. And in the last passage, what you do is that you write everything as a nice vector, right? So you have the input X there. And the Y is the Poisson noise, so it does not depend on the beta. So you ignore it, because in the next slide, go to the next slide, you take a derivative. Go ahead from here.
Yep, so we take a derivative to find the gradient, and we set gradient to 0 to find the maximum likelihood estimation. Yep, so eventually we'll realize that there's no closed form solution. So you have to resort to optimizers. And some optimizers, example, can be gradient ascent or descent, or iteratively reweighted least squares. Yep, so eventually run the model. And we have a MAE, which means mean absolute error, which measures how far predictions are from actual values on average. And the trained MAE is error on data the model learned from, and test MAE is error on unseen data. So this concludes that model generalizes well and maintains consistent accuracy between training and training sets. And
question: why do you use MAE and not MSE in this setting?
Because in Poisson model, predictions measure prediction accuracy in simple intuitive terms, and MAE complements Poisson deviance by giving a straightforward error measure in the same units as the data.
I mean, it's more like, can you go back to your least square? Go back a couple of slides. Let's see. No, stay there. Stay there. It's more. It's something a little bit subtler, right? So it's like here you assume to have a Poisson noise, right? And so think of it this way, right? So there is sort of a conjugate error for a certain distribution. Do you understand what I mean by conjugate? Like in Bayesian statistics, you have something like a conjugate prior. Or the idea is that some quantities fits well together, right? So if you are on a Gaussian distribution, right, in the argument of the exponential of the Gaussian distribution, you naturally have an L2 distance, right? So that means that the way of measuring the distance under, let's say, a linear regression model fits with the Gaussian assumption of the data and fits with the geometry that the distribution imposes, right? That the distance between 2 points is related to the L2 distance. When you are in this Poisson setting, right, then the L1 naturally connects to the regression model and to the distribution of the noise that you assume, okay? So it's more, it has to do with sort of the type of topology, the type of distribution that you use for modeling the process, okay? Go ahead. Don't use ChatGPT, right? ChatGPT says, "Oh, more natural, safer," but it's empty words, right? That you have to have some deep understanding of why the MAE fits the Poisson model, just as the MSC fits the Gaussian model. Okay, go ahead.
Okay, so next we have the mean Poisson deviance, which measures how well a Poisson model fits the data. So from the results that we generated, it provides a very good fit, and its predictions are well calibrated to the observed counts.
So this MDP, right, the MPD, right, is again it's a Gaussian distribution fit. So when you fit the residual, you want the residual to be Poisson distributed, right? Okay, go ahead.
And the low dispersion statistic, Poisson assumption of equal mean and variance is reasonable, and there's no over dispersion.
Okay, very good. Also here, this is very important, right? So because when we have a Gaussian distribution, we have two parameters. One is the mean, the other one is the variance. But in the Poisson distribution, we just have one, which is the intensity. So the intensity controls both the mean and the variance. So in order for you to observe a good Poissonity of your residual, whatever, you have to have that the mean and the variance are equal. Okay, that's why you use this fact that the mean and the variance are equal as an indicator that you have Poisson. Go ahead.
Okay, so next we have the graph of the observed Y and predicted value. So we can see that data points cluster near the diagonal red line, which shows minimum bias and strong predictive accuracy. And there's a slight underprediction at low values and minor overprediction at higher values. But overall, model effectively captures central tendencies. Next. So this is the residual to predicted value graph. And we can see that the residuals scatter randomly around plus minus 0.75, and there's symmetric variance and no trends or heteroscedasticity. And this shows a good model fit and adequacy. However, and there's also improvement from linear model where residuals scatter randomly at plus minus 2. And these are the coefficients. So out of all the many coefficients, these are the more prominent ones. And you can see that alcohol and sulfates, a unit increase in them will result in quality increase by 5.3% and 2.6% respectively. And for volatile acidity, chlorides, and total sulfur dioxide, increase in them will result in decrease in expected quality by 3.2%, 1.6%, and 2.2% respectively. So other features such as density, citric acid, pH show negligible or statistically insignificant effects. And overall, alcohol remains a stronger positive driver of quality, while volatile acidity and chlorides exert the most pronounced negative effects.
Okay, go ahead.
Okay, so now I will talk about the task 4, which is a Poisson with a regularization, which penalizes large weight. So in this will, sorry, previous slide, please. No mind, it's okay. So in this we'll test random 20 alpha values in between 10 to power of -4 and 10 power of 1. So why we choose random 20 is because I don't want to crash my own laptop. Yeah. So if you want a more robust kind of values, then we need a stronger GPU. Okay, next. Yeah, so this is the coefficient path from both L1 and L2. So on the left, you can see that for L1 regularization, many of the weights will drop sharply to 0 as the alpha increases. This is because L1 will reduce the number of variables by setting the coefficient to 0. While on the right, you can see for L2, it only shrinks the coefficient smoothly while retaining all the features in the model. Yeah, next. Yeah, so specifically at alpha equals to 0.0428, you can see that L1 eliminates 5 features, which are the citric acid, residual sugar, free sulfur dioxide, density, and pH level. So at this same alpha, although there are no L2 don't eliminate, but there are some where the weight is very small, where beta is below 0.02, such as the fixed acidity, citric acid residual, etc. Yeah, so on the right, you can see the top drivers of the variables with that alpha value. Next slide. Next slide, please. Yeah, so for one slide before. Okay, so key summary is basically L1 performs automatic feature selection by setting some coefficient to 0, producing a sparser and more interpretable model. However, it may eliminate useful but weaker features which can reduce the accuracy in some cases. Then for L2, it shrinks the coefficient smoothly while retaining all the features in the model, providing stability with predictors when predictors are correlated. However, when it keep all the features, even the weak one, it makes the model denser and harder to interpret. And when I run the model to test the MAE and the Poisson deviance, the mean Poisson deviance, it provides the same for both L1 and L2 at at 1 times 10 power of minus 4 alpha, which means that at a certain alpha level, both L1 and L2 are working generally the same, like equal level. So depends on whether your variables are correlated or not. You can choose whether to use L1 or L2.
Question here, the right hand side should be L2, right?
Oh, sorry, my bad. Yeah, the right hand side should be L2.
No problem, no problem.
Yeah.
Okay.
So I'll be explaining task 5, which is where we focus on the interaction terms and model extension. So the interaction terms capture the combined effects of two or more variables that cannot be explained by individual features alone. And these terms actually help us to better model nonlinear and complex relationships between features. So for instance, we consider the interaction between alcohol and volatile acidity, and then by creating a new feature, we can actually capture the combined effect of both features on the target variable, which is crucial for improving the model performance. Next. So we use polynomial features from scikit-learn to actually generate these interaction terms. So we set the degree to 2. That means that we only consider pairwise interaction between features, excluding higher order terms. And to ensure that our model works well with this feature, we do normalization using standard scalar, which brings all the feature onto the same scale, and then regularize our model with alpha 0.01 to prevent overfitting. And then similar to
explain this to me. So you do a standard scaling, right? But you do it with 0.01 to increase stability. Is that? Where did you get this trick from? Where did you get it?
I came up with the numbers myself. But in my next step, I'll be doing grid search to actually find the best value. But yeah,
I'm just thinking because you said that's interesting.
Yeah.
Okay. Go ahead. Let's see if I should believe you or not, or you have to retake the course. Go ahead.
Okay. So for our key evaluation matrix, I use MAE similar to what my colleague did to actually measure the average absolute difference between the predicted and the actual value. And a lower MAE actually indicate better model performance. I also rely on using mean Poisson deviance, which evaluates the goodness of fit for count-based model like the Poisson regression, and a lower value indicate that the model is a better fit to the data. Next. So we use the 5-fold CV to ensure that our model generalizes well to our unseen data and to prevent overfitting, as it splits the data into 5 different folds and tests the model on each fold, giving us an accurate and unbiased estimate of our model. So for our model, I actually perform grid search over some of the hyperparameter, which is polynomial degree, Poisson alpha, select percentile, and interaction only. So For poly degree, I choose between linear or include pairwise interactions. The
So
Poisson
nothing,
alpha,
no degree 2 or 3. Understood? Go ahead.
yeah, correct. And then the Poisson alpha, which is the regularization strength. I explained earlier the alpha value.
So
And
also the
then-
alpha you put in the grid search. Understood? Understood. Go
Yeah.
ahead.
And then the select percentile, where we use it for feature selection, where we rank features based on the mutual information with the target variable. So I use 25%, 50%, 75%, and 100%.
Come again. Then again about this mutual information stuff. Go back. Repeat that.
So the select percentile is where we rank the features based on their mutual information with the target variable. Yeah. So we only select maybe 25, 50, 75 of it. And
Okay.
then the interaction only controls whether we include those pairwise interaction or
Okay.
higher order
Okay.
interactions. Yeah.
But why the mutual information? Why the mutual information? I mean, just because it's a difficult quantity to evaluate, right? This mutual information.
Yeah, that's why I try to include it for my grid search.
I mean, because in order to evaluate the mutual information, you have to evaluate the joint distribution, right? And the joint distribution needs a lot of samples, right? Because
Yes.
so it's count based, but still, but the features are really, yeah. Yeah. So my point is that like we take the mean, the variance, the kurtosis, whatever. These are quantity that depends on summary statistics. They do not burn so many data samples to be evaluated. But for evaluating the mutual information, you need to have a joint distribution, which means that you have to estimate two-dimensional distribution. And this is, of course, this burns a lot of data, right? Because you're creating a lot of beans and you're creating a histogram over this volume. So I just wonder if statistically this is sufficiently robust with the number of data that you have. Go ahead. Let's see.
Okay, thank you.
You understand my point? You understand my point?
Yep, I understood your point.
Okay, go ahead.
Next slide. Yeah. So we'll examine how the model performs against the complexity. In the first case, where degree 1, where we only use the original features, where we increase the degree to 2, where we include pairwise interactions, we expected better results, where we use negative mean Poisson deviance as a metric. We actually see how the model do. So as you can see here, the negative mean Poisson deviance decreases as the model complexity increases, indicating that our model is actually fitting the data more accurately with increasing complexity.
Let me stop you there because I'm confused. So if you say degree 2 for me, it means that you consider up to a polynomial degree 2 in your scale, right? So you have the acidity and your acidity square. You have the alcohol and the alcohol square. But you said that this is not what you're doing, right? So what does degree 2 mean here?
Degree 2 means pairwise. So for example, acidity with alcohol.
I understand. But why here do you have why do you have interaction? Yes and no? Can you explain that to me?
Do I have interaction?
On the x-axis, I read degree 2 interactions, yes. And in degree 2 interactions, no. So what is the difference between degree 1 and degree 2 in this in the x-axis?
So the degree 1 is just the original features that we use for our data set.
But then there is, what does it mean degree 1 interaction, yes?
Yeah, degree 1 interaction, yes, means that we try to include higher order interactions.
But you just said that degree 1 there is only original features, right?
Yeah.
So what are you telling me? Am I not understanding something? I mean, it seems to me that you're contradicting yourself, right?
Yes.
So which one is it? Right?
Yeah.
The degree one that
Interaction true means that it does not include the power of the same variable.
So what I was saying is right.
Oh, okay. Yeah.
Right? What I was saying is right.
Okay. Yeah.
So how many points should I get from your presentation? Go ahead. Go ahead. So now it makes sense. Okay. Go ahead.
Next. So finally, we'll compare the performance of our Poisson regression model with interaction terms to the regularized model. And we can observe that our MAE of our interaction terms model was actually lower than that of L1 and L2 models, suggesting that adding the interaction terms actually improved the model's ability to predict the wide quality more accurately. And the Poisson deviance of the interaction terms was also lower than that of the L1 and L2 models. Further telling us that the interaction terms actually help the model to feed the data better. And overall, it just highlights that the adding interaction terms actually improve the performance, something that the regularization do not account for.
Question here, because when L1 kicks in, you know, which I would like to know, maybe you tell me in the final presentation, right? So when L1 kicks in, I would like to know how many features are decimated by the L1 model. Like the L1 model is going to push some of the coefficients to 0, right? And when you choose L1 and L2, you choose a certain coefficient for the regularization. So when you choose L1, you chose a certain regularization that sends some of the variable to 0. What I would like to see, right, are two things. So when you choose the L1, you choose a beta for L1 so that the number of total feature is the same as the number of original features, meaning that you add the interaction terms, right? But then you force the model to have the same complexity of the original model by setting, by having the same total number of parameters going to the inference model. I would like to know what is the accuracy and what the MAE and the Poisson deviance under this condition. Is this clear?
Nope.
Okay. I'll give you $1,000. You go out and you buy a CPU. And the CPU can take 10 inputs, which is, let's say, the number of original features. And then you train the model and you use the original features and you say, oh, I have this model with these 10 features. I have my regression. I put it into my CPU. I get this output. Okay. This is solution number one. I come and I'm another firm and I tell the company, I'm also going to give you a model with 10 features in input, but I'm going to improve your performance. How am I going to do that? I'm going to remove some of the original features and I'm going to add interaction terms. And I'm going to show you that by choosing interaction terms, I can have a better accuracy than using all the original features. Is this clear?
Yes.
So this is what I want to see. I want to see that you use the same number of total features, and you show me that by adding the correct interaction features, you can do better than using the original features. That's my question. Does it make sense?
Yeah, it makes sense.
Good. And for the L2, you can do something similar, right? For the L2, you can take all the features to be normalized, and then you look at, let's say, at the sum of the coefficients, and you want the sum of the coefficients to be less than 1. And then, given that the sum of the coefficient is less than 1, what is the relative importance of the features? And I want you to show me that the relative importance of the features is such that some of the interaction term, when you do ridge, will overtake the relative importance of the original features. So again, you go back to the point in which you have a set of features. You want to show that there is a particular interaction feature which overtake one of the original features, meaning that you can show me that using this interaction term does better than using a less informative original feature. Does it make sense?
Yes, it makes sense.
This is what I would like to see in the final presentation. Okay.
Oh, okay.
Good. Go ahead.
Yep.
Go ahead. This is fun. This is the fun part. Who's going to tell me about this and the EM algorithm that goes behind it?
Hello,
Is that
can you hear me?
hello? Yes.
Okay. So I will be covering the mixed Poisson regression models.
Why did they give you the
Oh.
hardest part? Because you're the best one in the group. Is that why?
No, we distributed 2 people here. So yeah,
I see.
we
Very good. Very good. The logic is
Okay.
impeccable. Go ahead.
So the mixed Poisson regression models is also known as the Poisson GLMMs. So the standard Poisson regression assumes that all observations shares the same global parameters. But in a real world, the data often has hidden differences between the groups. For example, in our presentation, the wines with higher alcohol levels may have slightly higher baseline quality. So to capture this unobserved difference, we introduce random effects into the model. So the mixed Poisson regression allows part of the model to vary across groups. So we can give a more realistic understanding about our data. Okay, next part. So why do we introduce random effects? The main reason for adding random effects is to handle over-dispersion. When the data's variance is greater than the Poisson model assumes. So in our data set, we observe that wine with different alcohol levels have different average quality scores. For example, wine in the higher alcohol group tend to have a higher mean quality than those in lower alcohol group. So even when acidity is the same, their baseline quality differs. So random effects allow the model to account for this kind of group level variation to improve both flexibility and generalization. Okay, next page. Oh no, the previous page, the previous. So we need to clarify the difference between fixed and random effects. Fixed effects describe the global relationship that applies to all data points. For instance, higher alcohol generally increases quality, but random effects, on the other hand, capture how different groups deviate from the overall trend. For example, high alcohol wines might have a slightly higher baseline quality level. The mixed model combines both fixed effects for the general problem, or not general pattern, and random effects for the group level difference, forming a more realistic hierarchical structure. Okay, next page. So the next page is about the model estimation and the setup. So we implemented both a standard Poisson model and a mixed Poisson model using the red wine quality dataset is the dataset we used. Our response variable was wine quality, and the predictors included alcohol, volatile acidity, sulfates, and critical acid.
Yeah.
We grouped the wines into 4 categories by alcohol level.
Yeah.
The low and medium low, medium high, and high. the mixed model includes random intercepts for alcohol group. We use the stats model function, Poisson-based mixed GLM, and optimized it using MAP estimation, which is efficient and stable for this type of model. Okay, next page. And this is our results. Let's first look at the results from standard Poisson regression. Alcohol has a positive coefficient at 0.0565, meaning higher alcohol content is associated with higher wine quality. Volatile acidity has a negative coefficient, so it indicates that higher acidity reduces the perceived quality. Sulfates shows a really small positive effect, while chloric acid is nearly zero and not statistically significant.
I mean, sulfates is half of the alcohol, but anyway, go ahead.
Okay. So next, the pseudo R squared is 0.0377,
Okay.
which is quite low, suggesting that the model explains only a small part of the variation, and that on model group differences may still exist. Okay, next page. So here is our mixed Poisson regression results.
Okay.
After introducing random intercepts by alcohol group, the mixed Poisson model produced very similar fixed effects coefficients. Alcohol around positive 0.0549, volatile acidity about negative 0.041, and sulfates around 0.021. The random variance components, however, were really small.
Okay.
As we can see in the intro. The previous page. No, the previous page. Okay. So the random variance components is quite small, which indicates that the variation between alcohol groups is minimal. This means that the mixed model slightly adjusts coefficient estimates, but overall, both models describes the same relationship. So in other words, there is only limited group level heterogeneity in this data set.
Heterogeneity.
Okay, next page. So here we have the comparison and takeaways. Comparing the two models, we can see that both identify the same key patterns. Alcohol increases wine quality. Volatile acidity decreases it. The mixed Poisson model, while more complex, accounts for potential variability between alcohol groups and can reduce over-dispersion. However, since the random effects variance was very small, the improvement in predictive accuracy is limited. In conclusion, mixed Poisson regression is especially useful when there are strong group level differences or repeated measurements. In our case, the groups are quite homogeneous, but the model still provides a more robust framework for understanding structured data. Okay.
Are you an expert in red wines? Do you drink a lot of red wine? What's your... Hello? Are you good? Are you an expert? Do you drink a lot of red wine? Are you a connoisseur of red wine?
Excuse me, can you repeat that?
I said, you drink a lot of red wine. Are you a connoisseur of red wines?
No.
I see. Yeah, because the clustering that you did by alcohol, it's not. I think you should have tried more red wines, right? And try to cluster them according to some other feature that you think, because maybe the alcohol. But I mean, I think you should experiment more by drinking red wine than writing only models. You know, you need some direct experimentation to decide the quality of the model, right?
Okay.
If you want any suggestion, let me know.
I think field research is better than desk research.
Right. So I thought you guys had two people on this part of the project, right? I only heard from one.
He said he had a midterm in the morning, and he just didn't sleep well last night. So I'll cover up his part. But he did really good on the coding and the slides. So I think it is quite fair.
Okay. Good. Okay, very good. Any other comments? Yeah, any comments from you guys? Yeah, so this last part is very tricky. So getting an improvement through these techniques, you need to finagle around quite a bit, right? So you cannot just rely on, yeah. Because, for example, you will want the, yeah. There are many possible ways of doing the last part, I think. You chose the alcohol level. Maybe there were some other parts that were more informative. We'll see the other groups. Okay, very good. Any other comments from you guys? Anything that you want to add? Yeah. Like, did you guys work well together? Did you share each other's experimentation? Did you use the same code? Just tell me a little bit about that.
We work together in a Google Colab, like everyone, I think. We wanted, or in the beginning, I wanted to meet together, but like everyone, and including myself, we are busy with midterms. It's like a busy week. But I think the cooperation went really well.
Very good.
And
Very good.
like for myself, at least, I haven't looked into everyone's work yet, but I will do it probably Friday. Then I have some time.
Bye. Yeah, okay. And after Friday, after you submit, you guys go drink some red wine so that you know you bond the group further.
Yeah.
Very good.
We'll do
Okay.
better research.
Exactly. Okay, very good, guys. I suggest I suggest a 3 minutes break. We just walk around and then we go to group 2. Okay, guys. If you have any questions, put them in the chat as usual. Okay. Ciao, guys. I'll see you in 3 minutes. Okay. Just walk around, drink some water, go to the toilet. I'll see you guys in 3 minutes. Ciao. Is the female? Hello, guys. So group B, guys, come. Group B. Is group B here?
So I'm from Group B, and we got some problems with challenge 2 because our first leader just
You're
said that
right.
he had to drop out the class. So
Don't worry.
we have another leader. However, the
go
second
ahead.
leader just disappeared and doesn't respond. He only created a line group and he just totally disappeared. That end, distribute a task for us, anything, or have any say anything. So we only have 3 people and we're just trying our best to do jobs now.
Very good, very good. Okay, so let's
So
not be
we're
negative.
if we
Yeah, go
can just
Give me what you guys have.
next week.
Thank you very much. So first of all, apologies, right? So it's not my responsibility, but so it's my responsibility to try to minimize this type of problems. But of course, there is a certain amount of randomness that I cannot account for. So apologies. You guys give me whatever you have, and then because this week some people have midterms. If he disappeared for a good reason, maybe he was sick, maybe if he disappeared for some good reason, then next week you guys present all together. Otherwise, when the inter evaluation comes, you guys just give me 0, and we try to move on. Okay. Again, first of all, apologies because we try to minimize this type of issues in the group formation. And as I said in the first part of the class, this is unavoidable. We do our best. This is life is. Let's be positive. You guys show me what you have. We're gonna learn something from what you guys did, and that's what matters. Go ahead.
Okay. Let me see. See, it seems that we only have 2 members in the chat now. So, okay. And this is what I personally have done now, because only 2 people have write the codes now, and the other people is missing. So I'm going to just talk about my part.
Okay.
I now just take in the data, and I just want to see how different things have any common things in this picture.
I will say,
No,
but that's
no.
linear regression, right? That's the linear regression part, correct?
Yep.
This is linear regression. Stay there a second. Boom. So there is a strong group, right, with large coefficient, with acidity, volatile acidic and citric acid. This is very interpretable, right? Because citric acid is an acid, right? Volatile acidity, again, acidity, and fixativity is there. Then there is a strong group with the dioxide, right? There is a free sulfur and total sulfur. Very good. Then pH and density. Why are they so strongly correlated with acidity? Good. And then quality is your last count. Alcohol content is correlated to what? To density. Very good, very good. In fact, you expect the alcohol content to be the most correlated with density, right? Do you know? I'll just show you because you have a bad experience. So I'll just show you something. Yeah.
Okay.
I'll just show you something. Right. This one here. I'll just show you something just because it's fun, okay? Because you guys had a bad experience, whatever. So this you take this thing here, right? Have you ever made alcohol? Have you ever experienced with fermentation? No?
No.
Okay, so you should do it before you die, right? It's one of those things to do in life is to ferment something, you know? We've been fermenting things for tens of thousands of years. You know, it's part of life is fermentation. So this is how you measure alcohol in a home setting. So basically you have this object, right, that is graduated, and you put a certain amount of alcohol inside the tube and you see how much this floats. And this is because the difference in density of the water and the fermented liquid is the best indicator of the alcohol level, okay? And so there is a natural gravity, which is the natural density of water, and whatever change you see in your home brew is related to the alcohol level. So that's why it makes sense. Go ahead.
Okay, so here you can see some features in the data sets, and you can see that like residual sugar, chlorides, and like sulfur dioxides contain noticeable outliers. Yeah, this is some of my findings.
Okay.
And now this part is not I wrote, but my teammate is gone now, so I'll just go to my part. And now I've just done task 3. And for the gradients, the sense I use atoms based, and it's like this. Because the learning rates can be, we can change the learning rates, because at first I just used the normal gradient ascent, and I found that so it doesn't meet my requirements, because maybe the learning rate, if I always put the learning rates in the same one, will turn out to be, the prediction is really bad. So I tried to use atom based, and now.
Well, just stay there. Just stay there a second. Just stay there a second.
Okay.
How did you land on Adam? Just ChatGPT? Like this formula is from ChatGPT?
Actually, I've learned it in another class, because we learned lots of machine learnings.
Very good. Very good. Very good.
So I know that this atom can change the learning rates.
So did you notice an improvement when you go from GD to Adam?
Actually, yes.
Okay, go ahead. Show me.
And here you can see that by using this, we can see the data we wanted, and we can see that our deviance is 119, and our IC is this big, this small. So it means that maybe this is not is quite good.
So how did you figure out that the GD was not good? Because you had multiple random restarts and you have very different outcomes.
Actually, when I use GD, here it just can't perform the numbers, because it's maybe it's because that the learning rate is too big, so it just broke out, and they can't get the number of beta.
And how did you choose the beta for Adam? Did you do some exploration or?
I'm not sure, actually.
You just fix it to 0.1 as everywhere, right?
Yep.
Okay, understood. Good, good, nice, nice. Go ahead, go ahead.
And now this is the two plots, and like other teams, most of them are the same like the other teams.
Yeah, because the quality is integer, right? So that's part of the challenge, right? Is that the quality is an integer. So when you observe are these raster plots. Yeah, go ahead.
Yep, and now this is some of the interpretations. So like here, if beta is 0.25, which means maybe it's 20% expected increase. Okay, so this is what I've done now.
Good, good. Let's see what the other person did on this collab.
He's not in the chat now.
Okay.
I don't know where he did. Yeah, so maybe our team just has me now.
You're a team of one. You know, you're an army of one.
Yep.
Yeah, very good. I mean, I think see what you guys can do by Friday, right? And then by next week is gonna be a new story, right? So
okay,
don't worry too much again. So I'm sorry that you had a bad experience.
Nah, it's fine.
You have a tough skin, huh? You have a tough skin.
Okay, yeah.
Okay, very good. Okay, so let's move on with group C. Hopefully, it's not going to be a negative experience as well. Yeah, it's very interesting, guys. These things are, we learn a lot from these type of things. Go ahead, guys. Go ahead.
Okay. Can you hear me?
Yes.
Okay. Wait a second. Okay. My name's Will, and this is our team member. We got Booster, and he's an wine expert or so-called alcoholic. I don't know. And Khalid and Ding Yuhen. And our background is fish and the wine. It's fish and wine. And Booster gonna tell you why it's fish and wine later. It's a pun. Yeah. So Booster.
Yes, hello. Well, we are first gonna go through a brief introduction about the problem and about our data. Then we're gonna show why linear regression on red wine the quality does not really work, and why you instead need to pair the red wine with fish or Poisson regression, which you normally don't do. You normally pair that with white wine and not red wine, but in this challenge, we're going to do it with red wine. That was the pun.
Jesus. Wow. Oh, gee, I'm crying.
After that, we're gonna introduce some extra features and also
to recover from the terrible pun. Give me a second to recover from the pun. Jesus. Yeah, because guy Poisson is French. It's
French for fish.
French, right? So if you guys didn't get the terrible pun, this was the.
It's a good pun.
And also the fact that you do not, when you eat fish, you eat it with white wine and not red wine. Red wine is for steaks and heavy meals.
I think maybe next time you do an hour of comedy, right? It seems that you're very good at comedy. So next time you take a rest from after midterm, you just tell us terrible jokes.
Wrong field.
Wrong field.
And then at the end, we're going to do the mixed models. Go ahead, next slide.
So here's my part starts. Next slide, please. Yeah, this is an introduction, like actually pretty simple overview. We will talk about why standard model fails, how Poisson regression fixes it, and how can we make it even more better in the end. Next slide, please. Next one. Yeah, here we'll talk about linear regression, like what it is. Actually, there was a lot told before, so I will just make it quick. There is one main important formula about weight that our model is finding for every feature, and times measurement of features. So the first beta 0 in this formula is just constant. You can see it in the table in statistics, and every next beta is the coefficient weight we found. And next slide, right? Here we can see with same plot team A showed that this linear regression works pretty badly, poorly, because in ideal way, how it should be with linear regression, these residuals versus fitted values graph should look like some sort of cloud. It would be called homoscedasticity, but here we have heteroscedasticity that shows us that it does not work.
Okay.
Yeah, let's go back a second just to discuss a second. Can you go back? So there is also the fact that the true values are integer and the predicted values will be continuous.
Yeah, because we can see it on the second graph, the predicted quality and actual quality. Like predicted quality can be between 4, 5, and 6, and actual is just a whole value. And yeah, it's also run for these statistics.
Yes, I also want to say that when you see this difference in supports, sometimes you see this sawtooth kind of errors, right? Because you have approximation, so the error just happens to the closest one. Go ahead.
Okay. In my part is about Poisson regression. And the first time I heard Poisson distribution is in a class called probability, and that's one of the most difficult course I ever had. And the other hard course for me is electromagnetism. I still dream about it. It's a nightmare. Okay, and I'm off topic. Sorry. And this slide define Poisson general linear model. And first, we are modeling count. So Y follows a Poisson distribution whose mean is lambda. And second, instead of modeling lambda directly, we model log lambda as a linear function like this. And doing this guarantee the expected value of lambda is greater than 0. So the predicted mean can never be negative. And these two formula at the bottom are the likelihood and the log likelihood we maximize to estimate beta. And in this setting, the log likelihood is concave. So standard convex optimization method will find a unique optimum. So in practice, we use IRLS, or so-called Fission scoring, and you can think of it as a Newton type method with adaptive weight. And it fits in in our fit, it converges in 4 iterations. So it indicates the model and the data are well behaved. And the group B used Adam. Okay.
Let me stop you there, right? That's why I was asking the group B, because the group B went their own direction and they tried to use Adam optimizer.
Yeah.
So in my mind, I was thinking like the comparison between the optimizer.
Yeah.
I think so if group B is here and they want to do something by next week, I think they can tell us about difference between optimizer. I think it'd be interesting. Go ahead, please.
Yeah. So should I talk about it? I do know that kind
Go
of
ahead.
Yeah. I think the gradient descent is moved step by step along the negative gradient, right? So you must choosing a learning rate. So the learning rate could not be too large, but if it's too small, it will take time, and the convergence can be slow. But using the RLS or its second order curvature, each step is slowed. Each step solve a closed form, like Group A has shown us. So it solve a closed form weight least square system. So typically it takes larger steps and needs fewer iterations. So in our cases, it only takes 4 iterations to.
But the iteration complexity should be much higher than Adam. That's why I was wondering, right? So I was wondering comparison between the optimizer. Go ahead.
Okay. And these two plots give an intuition for us why we are using log link. The left panel, the original count scale, the dot are observed count, and the orange curve is a fitted mean, and the relationship is curved, and that means it accelerates upward as x increases. In the right panel, when we look on a log scale, and the point lined up as a straight line, this shows us the log of the mean is approximately linear in x, which is exactly what Poisson GLM assumes. Yeah, and this also explains a multiplicative interpretation for coefficients like beta 1. And beta 1 is a additive change in the log scale, which becomes a multiplicative change in the original scale. So if beta 1 is 0.3, increasing x by 1, it multiplies the expected count by e to the power of 0.3, and that's approximately 1.35. And that means it increases about 35%. Yep.
Excellent.
So, in short, I would say Poisson GLM is a model of the log of the mean as a straight line, and the coefficient represent a multiplicative effect. Yep. And this is a coefficient table in the indicators. The deviance in the AIC should be as lower as possible. The lower, the better, but it's pretty huge, and I'll tell you why is that. And the coefficient is a beta, so I will discuss what these coefficient means. Okay, so let's start with the coefficient table at the top, and because the Poisson GLM uses a log length, so we interpret each coefficient multiplicatively. So if a plus 1 change in a feature multiplies expected outcome by e to a power of beta, right? So alcohol has beta approximately 0.049, and that means e to the power of 0.049 is about 1.05, and that means each plus 1 unit of alcohol increases the expected quality by about 5%. And you can see the chloride, the coefficient is negative. So that means the higher chloride reduce the expected quality. Yeah. And
question is like this consideration are after standardization, right? So you do standard scaling, right?
Yeah.
Good. Go ahead.
Okay. And the left plot is actual versus predicted. And even though the true quality is descriptive, and so the point appear in vertical bands, the overall relationship is monotonic. The higher actual score corresponds to higher predict mean. So it's kind of diagonalized. And the right one is Pearson residual histogram. Residual are centered near 0 with reasonable shape, suggesting no major systematic bias. And our variation over mean on trend data is 0.115, and that means our data is under dispersion. So we have to use robust Poisson regression because our data shows under dispersion, right? Which violate the ideal Poisson variance assumption. In such case, classical standard error can be too optimistic, and robust SE adjust uncertainty upward and make inference more conservative. So, but the coefficient don't change, just the standard error and the p values change. Yeah. And this is the HC0. HC0 is basic heterogeneity consistent. I mean hetero. Okay, I put a YouTube link here. I put a YouTube link here to show how to speak that word, and that's literally the reason why I don't like English, because it's too hard to pronounce. For like Chinese, you gotta memorize. You just gotta memorize maybe 3,000 characters and you're fluent in Chinese. But in English, you got this vocab. I don't know how to pronounce. It's
You have to share that. You have to share the sound. You have to share the sound when you share.
Yeah. Heteroscedasticity. Yeah, I guess so. Okay. So edge C is heteroscedasticity consistent. I know what it means. It's quantized variance, but it's not variance because variance is a constant, and this is not a constant. So maybe when the data point in some range is widely spread, but on the other hand, in some range is focused, and we'll say it's heteroscedasticity. Yeah. So SC0 is consistent covariance estimator. It doesn't rely on the Poisson variance equals to mean assumption. Instead, it used the empirical variable of residual to estimate the uncertainty. And this is the metric form of it, where the H is the expected information or Haitian matrix, and the S is the empirical covariance of the score contribution.
There are too many minus one. Yeah, there are too many minus one. There are too many minus ones here, right? Are you sure there are two minus one? Is there one minus one?
It's called sandwich estimator, so I think it's two. I think because it's more like a sandwich.
Yeah, because S is square, right? It's just that why do you apply the inverse twice?
I think it's two minus one here. I
mean, intuitively, I'm just arguing intuitively, right? I'm not. Yeah, but I believe you.
Okay.
Go ahead.
So the S, I think, in my interpretation, is like a sum of the outer product of per observation residual score. Yeah. So for a GLM, you will often see an equivalence expression like this. So H is like this, and the S and the H. So the Pearson residual is look like this. So in the former slides, we see the Pearson residual.
Yeah, but that's the point, right? So the size of this object is the size of the data set. So if your data set is 3,000 or 30,000, and the matrix is 30,000.
Yeah, yeah, it is. Okay, so
that's why I was asking about the inverse, right? Because the dimension remains so large of this estimator.
That's a point. That's a
because
that's a good point. I'll do some research on it later to see if it's 2 minus 1 there.
Yeah, please let us know. There is something. You understand what I mean, right? There is something fishy because
I do. It's too big.
It would not be practical, right? So if you have to correct, also, Anyway, we understand. Go ahead.
Yeah. Okay. So the key idea of it is to estimate the covariance of the actual residual variability, not from a possibly wrong variance model. Yeah. And this is a robust standard errors. You can see the coefficient is not changed from the last one, but the standard error changes and p-value changes. And this is Poisson with L1 regularization. And L1 makes the model simpler. We add an L1 penalty to the Poisson loss. The larger alpha, the more we encourage coefficient to be small, sometimes exactly 0. In the coefficient path plot, the left plot, and each line is one feature coefficient moving left, and moving left means increasing alpha. You can literally watch a line slide to 0. Those features are moved by lasso. And the CV table on the right scans the grid of alpha and compare the average mean Poisson deviance here. And the best alpha.
That your alpha goes to 0 that way instead of going to 0 this way, right? It's just confusing for me.
Yeah.
Go ahead.
Going 0 that way. So, so the best alpha is 0.01, and with the best, I would say best, and MPD is 0.069.
Let me think about this. Let me think about this. Do you do cross-validation for this value, or
Sorry, can you say that
do you
again?
do cross-validation for this plot or not?
Yes, I did do cross-validation.
Okay.
Yeah.
Okay. Then I believe you. Then I
Yeah,
believe
yeah.
you.
And you can see from this plot, the coefficient tend to hit 0 first are those very small magnitude or are high collinear with other. So if it's very small or very highly collinear, maybe tend to towards 0. Like in my collab, there's like sign saying what this is, but I don't know why I downloaded it and it disappeared. So I check it. The towards 0 include free sulfur dioxide or total sulfur dioxide or residual sugar or fixed acidity, and larger effects such as alcohol and sulfate and chloride, something like that. It typically remains non-zero.
Yeah, because my question is for you to what happens 10 to the minus 3, because you see that there is the blue and the brown line that they cross.
Yeah.
Because the blue coefficients were very close to 0, right?
Yeah.
And then it jumps up larger than the brown, and the brown goes to 0 before the blue does it, right? So that's a little bit fishy for me because it's the same with the gray and the green, right?
Yeah.
There is some collinearity there, right? Because
maybe
the model is sort of compensating something. Go ahead.
Okay. And the other one is a Poisson with L2 regularization. And L2 penalizes the squared size of coefficient, so it shrinks everyone a bit rather than deleting the feature. And this stabilizes the estimate, especially when a feature is correlated. In the path plot, all lines move smoothly towards 0 with larger alpha, but they don't flatten. They don't flatten at 0. That's just the key difference from L1. And the CV result shows the best alpha is 0.3 and the test MPD is 0.0688, which is best among the 3, the planned GLM, the L1 and L2. And this suggests many small contributor where L2 shrinkage improves generalization. Yeah, so this is my part.
Oh, now it's me again. Before we go into talking about how we can add interaction terms, so how these two interact, I will actually start by explaining what these different terms mean so that we might be able to understand where interactions might happen and where they might not. First of all, fixed acidity. That is acids that are normal to be found in the body, and as such, they usually have a nice taste. And in wines, they are attributed to being the acids that provide the sort of flavor of wine. So that there's different acids in this group, of course, but it could be like fruity, creamy, nutty, and sharpness and freshness. Those are the things that fixed acidity will be the reason for. Then you have volatile acidity. Volatile acidity is in most cases just bad because
volatility. You add in some syllable and just volatility. Go ahead.
Yeah, okay, the volatility.
Volatility. Go ahead.
Okay, but that is vinegar, which usually happens if you over ferment the wine. You get way too much of vinegar, and of course, vinegar is not a taste that is attributed to being not very nice, especially not in wine. It's a so-called wine fault.
What are you saying? Are you saying that balsamic vinegar is not good? Be careful.
No. I'm saying it's not something you want in wine.
Go ahead.
And citric acid, okay, that's a little self-explanatory. That's a lemon flavor. In the EU, it's banned to add it. If you add it, then it's not considered a wine. but in other countries it's not banned. And I'm guessing that this one is a little bit more complicated, as you can just it's something you probably add per taste of the different grapes that you're using. So it's probably a little bit complicated. Then there's sugar. The amount of sugar that is in the wine to begin with will also tell you how much alcohol you have in the end based on the density. So you mentioned the hydrometer, where you measure the density of your alcohol. And what you're actually trying to measure there is how much sugar there is left. So you take two measurements. You take it before you start fermentation, and you take a measurement after you've fermented it. And what you're left with is the residual sugar minus the total sugar that you added. It will be the sugar that's been converted, and the converted sugar has been converted into alcohol. And then there's some conversion factor there. But the residual sugar here is, of course, how sweet it is. Yeah. Then there's chlorides, which I've just called salt because that's what it is. It's supposed to be the amount of salt that's in the wine. And with all cooking, then usually a good taste becomes a balance of acidity, sweetness, and saltiness. So you would probably find that there are some interactions between, especially fixed acidity, sugar, and the salt, and that saltiness does not necessarily mean bad, but it can probably reach levels that makes it so that in the model it'll be seen as bad. Then there's the free and total sulfur dioxide. Sulfur dioxide is something you add in fermentation to prevent wine faults. So it is basically that you try to prevent that the wine oxidates. When it oxidates, it becomes more flat in the taste, so it just becomes tasting like old beer or a beer that's been sitting out in the sun for too long. So something you don't want. That's not the best taste. And it's also added to increase germ control, so that you make sure that your wine does not contain any bad bacteria and stuff like that.
Or fungi growth. Yeah. Go ahead.
Yeah. Density. As I said, this should be correlated with the sugar, because sugar is what mostly is in high concentration. It's in higher concentration usually, and it's what mostly changes the density of the water in your batch of wine. But other than that, I have no idea how density affects the taste of wine. I cannot say. And the same with pH. It cannot be seen, but in this little image, it does say that wet wine should be between 3 and 4 in pH. But I have no idea where that number comes from. It just seemed to be the normal number that people used. Then we have sulfates, which looking at when I searched it on Google, it would give me. It would try and correct me to sulfites, which I thought was a little bit weird. Then I searched about the difference, and it said that usually sulfates are detergents, so for bacteria control and fungi and stuff like that. And they're usually not used in food. So I was a little bit confused. But
usually is the keyword here. Yeah?
But yeah, it's a detergent, so it shouldn't be that good. And if people start adding it, it's probably a mark of them not being that good at fermenting, I would say. Because the sulfite should also just do the trick. Alcohol. I don't know what for wine what the taste in alcohol does, other than the taste of alcohol, which would be I think could be attributed to being a warm feeling if you get higher up in the alcohol percentages, but wine is not that high. And then, of course, lastly, there's the quality. So that was a quick rundown of all the different terms that we have been talking about and that we're going to talk about further. So,
do you want to give us a background on your knowledge? Did you ferment?
I have fermented. I've never made wine. I've made 2 batches of beer, 3 batches actually. I did one in high school as well. I've made cider and I have made 2 times mead. The first mead turned out to be very bad because it was my first try, and the second one was good before I left. At least right now it's aging in Denmark, so I don't know. Maybe it's good when I come home. And then
And you just fermented everything, some glass carboy, just the regular stuff of the
yeah.
So
Yeah,
no
I mean,
instrument. Go ahead.
Yeah, I mean, the cider was made on apples just plucked from trees, and I got a like a fermenting set from my parents and a Christmas.
So you use natural yeast for the you use natural yeast for the cider?
No, I bought the yeast.
Okay. So then you wipe off all the yeast, all the original yeast with some some pill, like some additive, and then
I added sulfur.
Sulfate.
Not sulfate, sulfites. That usually
like the purple peel, whatever. Okay, very good, very good. Yeah, I mean, as I said, you guys should all do some fermentation. It's one of the.
Okay. Yeah.
Oh, you have to make bread and you have to make wine. That's not the basis.
Bread here in Taiwan is not not the best.
Go ahead.
I'm Danish. I get to be mean about bread.
Listen, I should also get to be. Go ahead.
Yeah, sorry. Okay, so what we want to do now is interactions between different parameters in the model by adding, by basically taking different terms and multiplying them with each other. In degree 2, this means that you take 2 terms and multiply them with each other, or you have the power of 2 for one single parameter. And when I just ran this code, firstly, the graph on the left is just the original model for these residuals and the this actual versus predicted test. And then when I ran the code, I saw that it regressed. It did not become good. This is just with all the interaction terms of degree 2. So I was a little perplexed as to why this happened. So I tried. Next slide. Oh yeah, okay, yeah, and as we can see here, the p-values, all of them are insignificant. So there's nothing in the result that was actually good about. Like we found that nothing was good about the model. Next slide. So then I tried using it on the degree 1, which should give the same results as the original model, but it still is not very good, which perplexed me a little bit. So, and I didn't really know what to do. So then, next slide. Okay, I think there's a slide that's. Is it missing? Okay, never mind. Okay, now I get it. Never mind. Well, I realized then that I had not done all the robustness of the model, and I'd forgotten regularization. So when I actually used what my colleague had introduced some minutes ago, all of that code, we got a way better result. Something that actually looks like a Poisson distribution around 0. It's skewed to the left, which I cannot explain why, but at least on the actual versus predicted test, we see that there's a linear increase, which you would hope to see compared to as the other one. Okay, next slide. Okay, yeah. So then I wanted to see, does it change with degree? And what I mostly found that changing the degree, of course, changed the computation power to a lot more. It took a lot more time, like 30 minutes for degree 3 and 4 minutes for degree 2. So that was a little bit annoying. But what we find is that when I increase the degree, it would also introduce more terms. This is with the not the rich one, but the L1 coefficient. So there are some non-zero values that's been excluded. No, not some zero values that's been excluded from this. And I'm showing this one because it's basically the one that's easiest to show on a slide, as there is not as many variables as there would be for the other ones. There's a lot of them that again are non-significant, but we find that there are the volatile acidity and the sulfates and alcohol interaction are the two ones that are. No, is there one other that I'm forgetting? No, the total sulfide dioxide and sulfates is not significant. It's almost, but not. But yeah, we find that these volatile acidity and sulfates and alcohol are the only two ones that are significant in the model. I would say that this perplexed me as, I mean, I get the volatile acidity one. Having wine being more vinegary is not what you want your wine to be, but the sulfates and alcohol does seem a bit random. And when I went to degree 2, again, you see the volatile acidity, and you see, let me see if I can find it. Total, yeah, that's the only one you see basically. So it's the basically only a model doesn't really, it only really finds that there's a significant, that it can find a significant weight on volatile acidity, so how vinegary it is. Yeah, I don't in like comparing with the older model, it's not really that we could find any extra terms that were very significant. So, yeah, so there's not really anything. It didn't really lead to much doing in introducing these interaction terms. Is the conclusion of the segment basically.
Very good. Right. So, but when you did these experiments, so do you also check all the interaction terms for the degree 2? So,
yes.
So it was like the previous. I see. That's why it took so long, right? Because you also do all the interaction terms, and then
yeah. It wasn't. I had to redo some calculations. Yes.
Okay, got it.
Yes. Next slide, I think.
Yeah, I mean, we need to have a chemist here, right? There's going to be at some point some chemist that explains to us acids and base, how they interact with each other, or is some.
You need a biochemist for it.
Okay.
Okay, so I'll be talking about the mixed model next. Okay, so next slide. Okay, so firstly, what motivates the mixed model? There's a possible variance with and relationship between groups within a particular estimator. So that's what motivates the mixed model. So for my model this time around, I split alcohol into 4 different groups based on the alcohol level. Okay. And from the graph, we may observe certain differences between groups, and this mixed model may account for these differences and make it better than a normal fixed model. So the mixed model may also account for this over-dispersion where variance exceed mean, but for this time round, I did not include it, but I checked already, there's not much over-dispersion for this particular data set or feature. Next. So how it does it is through adding random effects to capture variance and also allow variance to differ across groups, basically. Okay, next. Moving into our model, so I've fitted a baseline model similarly to group A for comparison, and also but the original model already has a low Poisson deviance, so it might not be the best to show the effects of the mixed model. So as compared to the Poisson model, the mixed model actually has a slightly decrease in MAE, while a slight increase in Poisson deviance. So this shows that there might not actually be much unobserved group level variance between the alcohol groups, as the accuracy only increased slightly. This also means that most of the variance may already be explained by the alcohol feature, and that's why there's not much change in MAE or deviance. Okay, next. Okay, however, something that I found interesting was that there's a variance in the random intercept when we look further. This should signal that there might be certain variance between the groups, and the model should differ from the original one, unlike what was the result earlier. Okay, next. And however, again, after looking further, the random intercepts of group 1, 2, and 3 are actually rather close and does not vary much. So that explains for why the MAE and mean Poisson deviance barely changed. As for
group zero was the lowest alcohol level, right?
Yes, correct. Group 0 is the lowest alcohol level, the 25th percentile and below. So group 0 actually accounted for the previous slide, which was the variance based solely off group 0. So
got it.
I've kind of explored it further and not included here, but it may be due to the low baseline quality of group 0 and group 0 having the least variance. So group 0 actually have the lowest baseline compared to all the other groups. It also has the lowest top baseline, the top cap. Yeah, so this might result in why group 0 has a way greater deviance from the other groups.
It's interesting. I don't know if there is any specific. Yeah, because of course, it's very difficult to have sweet grapes, right? Because they need longer time, sunnier weathers, and so on. So I don't know if there is a clear correlation between having low quality and low alcohol. Very good. Yeah, because also you cannot add alcohol or sugar to the wine. Anyway, so it's interesting. Go ahead.
Yeah, that's all for this mixed model part. And so basically, couldn't find too much of a group deviance between the alcohol group itself, except from group 0. So it might not be the best mixed model. And yeah, that's all for the mixed model part.
Very good.
So in conclusion, we showed that linear regression doesn't really perform very well on count data. So instead, we tried to use Poisson regression, which improved the model, but most of the parameters that we have data for are insignificant. Then introducing interaction terms didn't really did not at all actually change the model, and we didn't introduce any interaction terms because most of them went to 0, or were insignificant results. And lastly, we had a mixed model where we found a weird relationship with the one group of alcohol, and maybe for future work we should have worked with the other groups, so not necessarily alcohol, and instead maybe I don't know, pH or fixed acidity.
I'll remember
to see if they have a different result.
Then there is also the other conclusion that maybe just the noise was too much, right? So it's not the Poisson count. Estimating the quality, maybe it's not that rigorous of a process, right? So there is also maybe the mapping from the qualities to the score.
I mean, it's also that
by many things, but not.
Yeah, I mean, I don't know if you've ever. I mean, the Vivino scores of everything is also not that accurate. I would say ever.
It's known that the scale is between 90 and 100, right? So, but
yeah, I think Vivino goes from 3 to 4. That's where you will find every wine ever. If it's 2.9, then it's really, really bad.
Okay, very good, guys. Yeah, good job, guys. Good job. Okay, very good. Yeah, excellent. Good. So, no more comments from me. If there is any other comment from the class, I suggest again a small break because my brain is trying to catch up. A small break because my brain is trying to catch up with all the information coming in. So yeah, again, just 3 minutes break. I'll see you back in 3 minutes. 12. We'll see you back at 12:13, and then we go with the next group. Okay, guys. See you back in 3 minutes.
most of it, and then the runouts. It's early season, so it's like not super. I think it could be fun, but there's some nice runs over there too. Super nice. That are less.
Yeah, I don't want to drop in here.
If you feel good, I mean, normally the entrance would be like this.
Maybe you could sneak through even there. Just like dry ski it a bit and then.
Dry ski it.
Yeah, like
What
dry
does
ski
dry
it.
ski mean?
That's when you're on the rocks.
Aha.
1, 2, 3, go. Then it's me on this bad boy here.
Do you ski in from there?
No, from there.
Yeah. 3, 2, 1. Nico drop. Kind of rocky. Rocky Balboa over here.
Oh wow, it's really rocky, huh? Are you gonna do trampoline style here?
Holy shit, that's rocky.
There's like no hold in the snow here. Okay, here's my drop in. Oh my god. Oh, you're like,
Nice to send him first, you know.
I don't know if you actually want to do that. The next one over looks really nice.
Yeah, okay, I'll take your advice. Hola.
Hola.
Hey, it looks super nice. Ebba, I think this is you.
Is this me?
Yeah, I think so.
Think so?
So like Nico gets this message from a girl.
Hello, guys.
Texted Nico without ever having met him before. I was like,
I want to get on the program, the topside program. I want to ski steep shit. I want to come down to the Alps.
this is not a
Guys,
metal.
Just watch.
guys. Very good. Very good. Okay, let's start over, guys. I think somebody left the microphone on, and remember, it was recorded, right? So hopefully nothing bad happened. Okay, well, you're not saying something too inappropriate. Okay, very good. So Group D, are you guys here?
Yeah.
Go ahead, Group D. Go ahead, Group D, whenever you're ready. I see.
Okay, hi everyone. So we're Group D, and here are our members. We only have 4 members because one of them is dropping the module, I think. So yeah, we just took over his part, and we will not be presenting the part about the interaction terms today because that member is feeling unwell, so he wasn't able to complete his part. Okay, so diving right into it. Next slide, please. So part A will be on dataset inspection. So the target histogram actually shows that wine quality is discrete and bounded between 3 and 8. Most observations are at quality 5 and 6, which confirms that the response is non-negative, integer skewed and slightly right, integer valued and slightly right skewed. So this violates the assumption that continuous normal residuals expected by ordinary least squares, and also foreshadows the need for a Poisson type model. Then the correlation matrix actually indicates that alcohol and sulfates have the strongest positive correlation with quality. Volatile acidity is moderately negatively correlated with quality, and the other predictors show weak linear relationships, which suggest limited linear explanatory power overall. Next slide. Yeah, so the mean square error is at 0.39 and the R-square score is 0.403. These actually indicate that a moderate linear fit, where about 40% of the variance in quality is explained by the predictors. From the fitted versus actual plot, the points roughly follow a diagonal trend, but the spread widens for higher scores. So this actually shows that OLS underpredicts high quality wines. Then from the residuals versus fitted plot, the fan-shaped pattern shows a heteroscedasticity, which
You
actually
almost did it. You almost did it. Go ahead.
which is the situation where the variance of the errors in a regression model is not constant across all observations. So in this case, the residual variance increases with fitted value. Next slide. Wait, the previous slide, I think. Yeah, so the residuals are approximately normal as confirmed visually by the QQ plot. No negative predictions were produced, and these results indicate violations of the constant variance assumption and suggest that OLS is not suitable for modeling discrete, non-negative count data, motivating the use of Poisson regression in next section. So the next section, next slide please, would be on the core Poisson model. So the log likelihood function is derived from the likelihood function, as already presented by other groups earlier on. The IRLS method repeatedly performs weighted least square updates until convergence. So we used around 4 iterations, and this showed that the algorithm converged quite quickly and stably. The results of the estimated coefficients and their statistical significance are shown in the table. So according to the p-values, only 3 predictors are statistically significant at the 5% level, and the signs and the values of the estimated coefficients tell us the effect each predictor has on expected quality. Then as for the deviance, it indicates that most residual variation, it indicates modest residual variation where smaller values equals to better fit. Then from the AIC, it serves as a baseline to be compared to the penalized models in subsequent parts. Next slide.
This AIC, can I ask you, like, what do you know about the AIC? We didn't do it in class, right? Do you know a little bit where it comes from? What does it mean? No. Yes? No.
It is...
no guessing, right? If you don't know, just say I don't know. It's okay.
I think it just estimates the prediction error, I think. Yeah.
Okay, but
Yeah. So anyway,
what is it gonna do? Estimate? Of course, I mean, doesn't matter. Just next time we discuss it. Okay.
okay. Onto residual analysis. From the residual plot, we see that the points are centered roughly around 0 with no clear curvature, indicating that the mean variance relationship is captured reasonably. The discrete striped pattern occurs because one quality is an integer value outcome. From the predicted versus actual plot, the points cluster along the 45-degree line, confirming that the predicted counts follow observed scores, even though the spread suggests some under-dispersion or missing predictors. Next slide. Based on the results displaying the multiplicative interpretation of the coefficients, the predictors with positive coefficients increase the expected count. So in particular, sulfates and alcohol have positive significant effects where each unit of alcohol increase raises the expected quality by approximately 5%, and each 1 unit increase in sulfates raises it by 16%. And conversely, a 1 unit increase in volatile acidity reduces the expected quality by 20%. Then as for the predictors with negative coefficients, it decreases the expected count respectively. Yeah, and the non-significant predictors like density, citric acid, and pH show weak evidence of effect within this dataset. Now I'll be passing the time to Part C's member.
It sounds like the Senate or something. You give the reminder of your time to your colleague. Go ahead.
Yeah.
What's the word that they use in the Senate? I'll recede, I'll regress. Anyway, go ahead. I'll remit the remainder of your time. Go ahead.
And next is Poisson regression with regularization. Yeah, it's it adds the sum of the absolute value of model coefficient as this penalty to the loss function, and it can drive some coefficient to 0, and its penalty stress depends on the parameter alpha. And to see its effects on the coefficient, I choose the interval from 0.001 to 10 and divide it into 15 parts in a log space, and it results in 9 charts in a corner. Yeah. We can see some coefficient cut down to 0. And next page. we can see also regularization is as the sum of the square coefficient as the penalty to its loss function, and it won't cut out the coefficient to 0. Instead, it shrinks if it coefficient towards 0. And also we can see the line charts. And L1 and L2 regularization can help us to solve the problem of overfitting. This time we don't divide the data set into training data and test data. So maybe I should use K4 next time to verify its generalization.
You should do CV, right? You should do cross validation. Go ahead.
Next file is another member. So
Go ahead, guys.
The member for party got a high fever today, so he will present next week.
Okay, very good, very good. Hopefully he survived until next week. Otherwise,
yeah, he got serious 39-degree fever. Yeah, and for my part, it's part E. We evaluate whether AD mix effects improve modeling of the red wine quality scores. We compare a fixed effect Poisson baseline against Poisson GLMMs with random intercepts and a negative binomial GLMM. We also try several group schemes, density being 3, for volatile acidity extremes, sulfate extremes, and alcohol quartiles. And our target quality is discrete, so Poisson type models are appropriate. If there is talent heterogeneity between groups, a GLMM should produce a lower AIC than the fixed effects Poisson and estimate a non-zero random effect variance without hitting a singular fit. Those are the signals we are looking for.
okay.
And for our method overview, first we feed a fixed effects Poisson and check Pearson dispersion to diagnose over dispersion. Then we feed Poisson GLMM with random intercepts, and the sulfate 2 groups split at a random slope on alcohol. As a robustness check, we try NBGLMM. If that fails, we use Poisson and OLRE. We compare AIC and visualize to see multiplicative group shift. And this is our pipeline. And the
let me pass this. Let me pass this. Okay. No. Go back. Here, let me just pass a second, right?
Okay.
Sulfur and alcohol, 4 beans, and sulfur 2 beans. AIC. Why don't you have a number there? Yeah, can you explain this? This table is a mess. What is this? What's happening in this table? So the first model doesn't have group. Yeah, go ahead. Tell me.
Okay. Because I copy it from my code results, and I don't know why some block is empty. Yeah, so some data is missing.
So whose fault is it? My fault? What are we supposed to do?
Maybe it's my setting problem on my code.
Do you want to check a second if you have the numbers, and then we go back, or maybe you tell me next week as well? Yeah, I understand everything. It's just that the numbers missing. Go ahead. What do you want to do? Next week. Go ahead now. Next week you tell me again. Go ahead.
Okay. And this is the result from that incomplete chart. Yeah. And for the first one is GLMM. Bars are very close to 1.0 across all density. After covariate density groups don't shift the overall level. AIC is not lower than FE, and the fit is singular, means the random effect shrinks to 0.
The left is for density, the right is for VA. What is it? The volume.
This one.
Yeah, the one that is density, and the right one is alcohol. What is it?
The left one is
density.
Density. Left one is density.
The right one is VA, volume, alcohol. What is VA?
VA.
Volatile acidity.
Yeah.
Got it. Go ahead.
And the conclusion for the left picture is the density split doesn't form meaningful structure for quality. And for the right one, both high and low groups sit near 1.0 on the multiplicative scale. Random intercept variance is approach 0, and the fit is singular, with FE dispersion smaller than 1. NB and OLRE brings no gain. And for this, it's about random slope. The left one is about random slope on alcohol. On the order of a few percent. However, AIC is higher than FE, and the fit is near singular with a very small random intercept variance. And the right one is the 95% confidence intervals overlap 1.0 for all groups, so differences are not statistically distinct. Yep. So the takeaway from this is FE Poisson dispersion smaller than 1, so no over dispersion. NB and OLRE offers no improvement. And my conclusion is keep FE Poisson as the primary model. Use GLMM only as a robustness check.
The pronunciation is Poisson, please. Don't say Poisson, say Poisson, because there is Poisson also like model poisoning. So it's the French pronunciation, so it's Poisson. Yeah, just because it's confused.
Okay.
Go ahead.
Yeah, and this is our work distribution.
And yeah, somebody was sick. Okay, so I'll see you guys next time. We'll wait next time to give you a grade. Very good. Yeah, good job.
Great, thank you.
Thank you. Okay, Group E, come guys. Group E, come. I would like to convey to you guys that this is really a marathon for me because I have to stay attentive for 3 hours or something. My old brain is really challenged. Go ahead, guys. I hope I'll do a good job until the end. I hope. Yeah, if group D can stop sharing, then the other group can take over. Okay. Just your microphone is a little bit screwed up. Can you check that the settings are okay? Listen.
No.
Still terrible. Sounds like you're underwater and drowning. Under. I understood. We'll just wait. The rest seems like a message from outer space.
Okay, so now can you hear me clearly now?
So. Try again. Say something.
Hello.
It's okay. Let's see. Otherwise, I'll ask you to join with the phone and use the phone microphone, please. Go ahead.
Okay, so I am Javier and we are Group E, and we got the name Team Emo because we will have to do the presentation in the midterm intensive session. Yeah, so anyway, we are going to start our presentation now for this Poisson regression and count modeling. We also got Chou Jian-an, Yang Zu-an, Yang Kaiming, Zhen Lici in our group. And also for today's presentation, we are going to firstly give an overview for the data and then show our work, including linear regression, Poisson regression, and regularized Poisson, and also do the interaction terms and Miss Poisson parts. And in the end, we will make a briefly comparison and discussion about our topic. Okay, so first let's give a quick look of our project. We are going to identify limitations of linear regression first, and then evaluate the benefits of the Poisson and GLM in and our data set used is the red line quality data set. Okay.
Okay, so on this slide, we begin by exploring the red wine quality dataset. And the bar chart on the picture shows the distribution of the target variable quality. And as we can see, most samples are rated 5 or 6, while only a few reach 3, 4, or 7 or 8. And this pattern confirms that the response variable is discrete, non-negative, and writes good. Sorry, excuse me. Am I the only one see the screen as a
I was gonna see like the screen is cut off for some reason. I don't know if you're using something. Yeah, try to go into presentation mode. Click. Let's see what happens. It's still clipped. Is it better or is it clipped?
Yeah, it's better.
Okay, go ahead.
Okay, and since the quality score takes on integer values and is not normally distributed, and this already suggests that the standard linear regression model, which assumes continuous, normally distributed outcomes, may not be appropriate. And therefore, this visualization helps motivate the use of count-basis models such as Poisson regression or later on. And so this is why this challenge exists. Next page. And here we examine several key predictors that are commonly related to wine quality, including alcohol, volatile acidity, and sulfates, citric acid, and density. And from these histograms, we can see that most features are not normally distributed. And alcohol and sulfates are strongly right good, meaning most wines have low values with a few high extremes. And volatile acidity also shows a moderate right score, and density is nearly symmetric, while citric and acid is slightly skewed but closer to uniform. And these patterns tell us that the dataset violates one of the key OLS assumptions, and namely that predictors and residuals should follow approximately normal distribution. In short, the dataset contains nonlinear and skew relationships and that are not ideal for a simple linear regression model. Next page.
This one here, let me just correct you a little bit, right? Because like the fact that the each of the parameters, they are not Gaussian, does not necessarily mean that the linear model doesn't work, right? It's just that, as I was saying before, there is sort of a conjugate idea, right? There's also sort of an idea that if the features are Gaussian and the loss is MSE, then you will expect the linear model to work well. But of course, the linear model just talk about the mapping between the X and the Y, right? So just a comment, but go ahead.
Okay. So after inspecting the data as we build a linear regression based model and following the OLS equation, y equals to the features times some beta and plus some epsilon, and where epsilon is assumed to follow a normal distribution with constant variance. And results show several issues. The model occasionally produced negative predictors for low quality wines.
Correct.
And which makes no sense because quality cannot be negative, and the residuals are not normally distributed, and the residual plots reveal a clear heteroskew patterns, and meaning the variance of the errors grows with the predicted values. And in terms of metrics, our model achieved roughly MSE equals to 0.59 and R squared roughly equals to 0.26, and which indicates weak explanatory power. And
Right,
overall, this tells us
if the
that
MSE, just think about it. If the MSE is is larger than 0.5, and the distance between two scores is 1, it means that you're
because we
often
got higher like 5 and 6
correct, right?
quality wines more. Okay, so overall, this tells us that OS violates the fundamental assumption for modern discrete count like this data. Next page. Okay, so here we visualize those findings more clearly. On the left, the residual distribution shows that the arrows are not perfectly symmetric and the curve is slightly skewed to the right, suggesting that the model tends to underpredict higher scores. On the right, the scatter plot of actual vs predicted quality confirms this, and wines rated 7 or 8 or 3 or 4 are predicted around 6 or 5, and meaning the model underestimate high quality samples and low quality samples. And this bias towards the mean is typical behavior of OLS when applied to discrete data, because it fits a straight line through a screw-bounded target, and the model cannot stretch enough to match extreme values, resulting in symmetric underprediction of high counts and potentially negative predictor for low counts, like quality with 1 or 2 will be negative, but it doesn't show in this plot because we don't have that kind of quality 1 here. And this observation motivates the move to a log linear Poisson model, and which ensures that all predicted values remain positive and naturally scaled with the mean of the data and the integers as well. Next page. So here we summarize why linear regression model fails. The OLS assumption of continuous and Gaussian distribution outcomes are not valid for our discrete target, and the quality scores are non-negative integers, not continuous mean measurements. The model cannot guarantee positive prediction, leading to unrealistic results, and the error variance depends on the mean, creating violates OLS theory. So the limitation explain why we need to use Poisson or other regression on this kind of task. Next page.
Hello, can you hear me?
Yeah.
Okay, and also I'm doing the Poisson regression part. So the first thing we need to discuss is about why do we choosing the Poisson discretion, and the reason why we use Poisson, because in the last page it's just say because the thing we want to predict, which is a quality score, is discrete, and we're using log link to ensure that lambda is over 0, which means because in the score there will never be a negative score when we do the quality scores. So we use the log link, but why is Poisson? Why is Poisson? Because like for the model of the Poisson regression, it's assume that it's observed target value y and independent count event abrupt or random event, which is exactly fit what our data set is. So maybe this will be a good way to do the regression. So and then we do the coding part, and then it's the graph. And this graph is is the basic assumption of Poisson fit the data we have. So this is what this graph is looking at. And what is the basic assumption of Poisson, which is expect is equal to the variance x.
Correct.
Has it right here? No. Okay. And the random distribution of residual. And obviously, the graph shows that in our data set, it's not quite good to use Poisson regression to do the research, because the most significant problem is under dispersion. Really on this, because it's like a band type distribution of these graphs. Graphic. Okay, next page. Okay, and for this graph, we are trying to evaluate is the accuracy of the alpha we're using MAE for the for this thing, and obviously it seems like the predicting have been not that accurate, because we can see that there's only a few pointers on the line. Yeah.
What's the size of the test set here? 7? Why don't you use a few hundred for the test set? Why is the test set so small? Anyway, go ahead, please. Use more data for your test set, right?
No. It was just actually quality score. It's a score.
Yeah, but why do you have so few points, right? You should have more points in the graph, right? Unless, you know what I mean?
I know what you mean. I will check it later.
Question. Here, did you quantize the predicted score to be integers, right? So each point is a density then, right?
Yeah.
And okay, try to use the size. Not the color.
Okay, I'll do it next time.
Because the color is not very readable. Because when I saw it the first time, I thought it was just 1 point. Then I realized that it's an intensity. But try to use some other so you understand how many points.
Okay, I will check it later.
Very good. Go ahead.
Okay, and but like we use MAE to doing this because for 2 reasons. Because the first reason is that MAE use same unit.
Go ahead. Yeah. And what's the second reason?
And the second reason is that robustness of the outlier. Because when we go into the statistic way of the Poisson distribution, the Poisson distribution was when using in practical way, it was to tackle with extreme value against the outlier. So MAE will be a better way to do this because MAE will lower the penalty when we're training the model. That was the way how I interpreted it. Okay, next page. Thank you. And then we do the MLE and the data. Well, while I doing the MLE, because there's a thing that's called the likelihood function. And actually, I'm not actually understanding what is the mathematical way that is doing. Like I'm not actually know how is it working on, but I trying to find out what this is doing. But actually, the only thing I can do is to know how to use it. But except to learn what is it. Yep. So the thing I learned from this was that beta will stand for the log expect rate deviation, which you use for log link. The first thing I learned from this. And so we assume that the variable we are predicting is Poisson distribution and try to optimize the efficiency of beta to get the maximized beta hat, which is somewhere around in the graphs. And then we calculate the P and standard error to make sure it's statistically reliable. But the question is, in the first page, we say the distribution of it is under dispersion. It's under dispersion. So the p-value will be very sensitive for it. So maybe the p-value is not that reliable for it, but I'm still using p to evaluate for the following graphs. And okay, next page. Next page. So we choose. I only pause to picture here, and I don't know why the title is being hidden. And so the thing I use is marginal effect of volatile acidity and marginal effect of suffix. This is the picture, and which is using the. Wait me a moment. Which is using the multiplicative interpretation, which is something like this. This was saying that when you increase 1 unit and what was the quality rate will, something like that. When you increase 1 unit of a suffix and then the expect quality score will increase in the percentage. Okay, next page. And next page, please. And in this part, this one. And this part, we're trying to regularize in the Poisson regression by the last order reach, which is L1 and L2, to since to regularizing the Poisson regression, why do we need to do this? Because for some reason, because when you're training the model, there will be a 3 problem while you're training. The first one and the most common one is overfitting.
Of course.
Overfitting. First one, and the second one is you will trying to automatic feature selection. You want to selecting some feature which less is important or not. So that was the 2 main problem when I train the models. So the way how to deal with it is to trying to regulate it, regulate it. Okay, and so for the L1, which is the lasso, which is used for the feature selection, it will add the penalty based on the sum of the absolute value of the coefficient affect on its own beta. But when I doing this part, I have a question is I'm not actually know about what does the penalty do. Yeah. So
what do you mean? So the penalty is like a certain loss, right? And you add it to the loss.
Oh, okay. Because like when I'm searching for some research, I do some research or ask AI and say penalty, I was thinking about what was it actually doing when you're training the model.
Did you attend class when I was doing lasso regression? Did you attend class?
Yeah, I attended the class.
Were you paying attention to the class, or were you?
I paid attention to the class, but like some part you didn't understand it, and you was like, what that?
So you say it's my fault that I didn't explain well enough.
It's my fault. I'm not understanding it. My fault. Now I'm trying to find out what that actually is, but like
the point, let me just say, the formulation is very simple. You have a certain loss that depends on the y and the y hat. Then you do plus a certain lambda, right? Then the sum of the absolute value of the coefficient. The value of the lambda decides the severity of the penalty. So that when you calculate the loss, the value of the model parameters themselves play a role in the loss. And the importance of this part is controlled by a hyperparameter, which is the lambda. That's it. Go ahead.
Oh, okay. Thank you so much. Okay, so we're doing the lasso reach one, and the lasso is to affect its own beta, and the reach one will shrink all the coefficients C. So the result will be like the L1 will select which is more important, and the L2 will do the coefficient shrinkage, which is right in here in the next page. So, okay, so the result will be something like this. And for the L1, and you can see like the fixed acidity, I think that is much more importance for the L1 one. And the L2, you can see that it will not in the 0 line. It will not shrinking into the 0 line, although this was shrink very slowly. Yep. So that is next page.
Okay, go ahead. This looks interesting. Very artistic. Tell me about this figure.
That's also on my part.
Who's coming next to tell me about this plot? Is everybody from group here? Yeah. Yes. Can you use the microphone? We're waiting for you. Are you muted for some reason? Okay. So what you can do is you can try to connect from the phone, and then use the phone to talk to us. Is the person in charge of the last part here? So maybe we can switch, and then comes back later. Is the person in charge of
this is the final part.
Okay. So you didn't do the part on the mixed model, right?
Yeah. I mean, the person doing this part has something to do today, so he can presentate, and the person will present for him is now having microphone issue.
That's what happens when you rely on.
No, we have to the mixed part, but like this part and the mixed part was for one people who do it.
I understand.
And,
I understand.
and that guy was some issue today, and
we can move to next week if you guys want, right? So if it's no problem for them.
Can you just use your phone and without AirPod?
Let's see. Let's see. I mean, I can try to improvise and present for him, but I think it's I shouldn't. It's clear that here you divided the three different alcohol levels, right? And then sulfates and so on and so forth. And then you plot the mean quality versus the pH, and you use the alcohol as a label. So there was sort of some sort of clustering, right? Some sort of nonlinear, trying to infer some nonlinear interaction between the terms.
I think I can try to present. So a traditional Poisson model assumes that each variable affects wine quality independently, but in reality, chemical features like alcohol and content and acidity often interact with each other. So therefore, we introduce interaction terms to capture this nonlinear relationship between variables. And so in this code, we select several key features such as alcohol, volatile acid, citric acid, and residual sugar, and sulfates, and pH, and something like that. An example include this in the chart show. So we first train a baseline Poisson model using only the original feature, and then compare it with the model that included interaction terms. Next page.
Got it. I understand. That's why the quality prediction is not an integer. Got it. Go ahead.
Yeah, so the results shows that after adding interaction terms, the mean square error decreases by about 6%, indicates a clear improvement in predictive performance. And among all the most influent interaction was alcohol multiplied by volatile acid, I think, and showing that the combined effort has the strongest impact on the wine quality. However, adding interaction can increase model complexity, so this consume more time to train and predict. To prevent overfitting, the program applied cross-validation and turned the regularization parameter alpha. And the optimal alpha value was found to be around 0.5, which provides a good balance between accuracy and stability. So in the sixth part, the traditional Poisson regression assumes that all samples share the same set of parameters. However, in reality, like this kind of data, different groups can have different underlying characteristic. And for example, here the different alcohol concentration may have distinct baseline quality labels. To account for such group difference, we introduce random effects and allowing each group to have its own intercept or dividation. And in this program, the alcohol contains divided into 4 categories: low, medium, high, and very high. So,
let's see if Kamin wants to come back. I think he figured out how to use the microphone. Kamin, are you with us?
Hello, can you hear me?
Yes, very good.
Okay, so
can I tell you a trick? Next time, you can take a speaker and plug in the speaker in the microphone, and every actuator is also a sensor. So you can use a speaker as a microphone. Make a suggestion for next time. Okay, go ahead.
Okay, so in the sixth part, the traditional Poisson regression assumes that all samples share the same set of parameters. However, in reality, especially for data like wine quality, different groups can have different underlying characteristics. For example, wines with different alcohol concentrations may have distinct baseline quality levels. To account for such group differences, we introduce random effects, allowing each group to have its own intercept or deviation. So in this program, the alcohol content was divided into 4 categories: low, medium, high, and very high. A separate Poisson model was then fitted for each group to observe the differences in their mean quality scores and intercepts. Next slide, please. Next slide, please. So the results show that as alcohol concentration increased, the average quality also rose, with the intercept shifting from around minus 0.15 up to 0.48. This clear upward trend demonstrates that there are indeed meaningful differences between groups. Differences that a mixed model is specifically designed to capture as random effects. Additionally, we examine the issue of over-dispersion. In theory, the variance of a Poisson model should equal its mean, but the calculated dispersion parameter was approximately 1.28, indicating moderate over-dispersion. So this means the standard Poisson model underestimates variability, while the mixed model can better correct for this problem. And next slide, please. In this slide, we summarize the key differences among the 4 models. So the linear regression model performs poorly on count data because it can produce negative predictions and assumes normally distributed errors. And the Poisson model corrects this issue by ensuring all predictions are positive and interpretable in terms of expected counts. And when we add regularization, the model becomes more stable and avoids overfitting. Finally, the mixed Poisson model provides the highest level of realism and flexibility by accounting for unobserving group level variations. And next slide, please. So, in conclusion, we learned that model choice must depend on nature of the data. The Poisson model ensures positivity, regularization improves stability and interpretability, and mixed models capture random effects between groups. This challenge told us that the successful modeling isn't just about getting a lower MSE, it's about understanding the statistical assumptions and the data distribution behind each method. And next slide. Thanks for listening.
Very good, very good. Okay, thank you so much, guys. Good job. I think, yeah, good. So you also noticed the no alcohol on medium alcohol change of model. Yeah, very good, guys, very good. Anything else that you guys want to say? Did you, yeah, any other comment on the project? Okay, very good, very good. Okay, very good, guys. All these lectures are always, very tiring for my brain. So toward the end of it, it's, yeah, I'll try to do my best, let's say. But of course, it's a lot of output. So just by Friday, you'll submit the report as usual. Then we send out the evaluation forms, and then we proceed as usual. Okay, and then from after the midterm, right? So after this week, you'll be able to choose your own groups. So you so far work with 3 sets of people. So you should have met around 15, 12 new people. And so when you form the group, you should be able to choose a subset to form your own group. And we can enter the next phase of the class. So hopefully no more struggling with teammates not being responsive or people dropping out of the class. Okay, as always, we try to do our best with this respect. Okay, very good. I'm gonna stop recording. Next time we're gonna do logistic regression. We're gonna assign the new challenge on Friday, and then if you have any other question, I'm gonna be here online and say goodbye to the people on YouTube. Remember to subscribe, click like, leave a comment, and I don't have a Patreon, but if you want to send money, you can just give me straight up cash. And we see each other soon. Okay, guys. Ciao, ciao.